So NMR is nuclear magnetic resonance. Certain nuclei have a magnetic moment that can be detected by our instruments. And so what we can do is notice that alignment with an external magnetic field and, more importantly, the time it takes to relax back to it after a radio burst. And so it is that kind of studying through multiple math and calculations and stuff like that that gets our end result. So ultimately, our nuclei have two possible spin states, alpha and beta. And so what can happen is we drop our samples into a magnet, and what will happen is our nuclei will align to that magnetic field. Once it's aligned with that magnetic field, we can then fire radio frequencies at our sample. Those radio frequencies will knock the alignment of the nuclei off axis, and we can detect that subtle change in total magnetic fields. That, and then timing that, allows us to understand something about where those nuclei are located and their general environment. So if we look at just kind of a general idea, if we take a look at a nucleus, and we say, here it is, we got a nucleus spinning in a particular direction. Well, we would hit this with radio frequencies, and that now spins slightly off axis. Okay, so instead of being aligned with the external magnetic field, it's slightly off. We can detect that difference. And more importantly, what we can detect is that that magnetic field or that sample will slowly eventually revert back to being in alignment. Okay? And it is that kind of correlation that can give us information about the environment. For instance, if there were a bunch of electrons around it, shielding it, well, then I would have to use a different radio frequency, and that's going to change how much how the time it takes to relax back, and we can correlate that into some structural information. Okay. The other thing that can be beneficial, and we see this when we talk about splitting, is that if we have multiple nuclei near each other, those nuclei can now affect each other's spin, and that can change our signal as well. Okay, so that's kind of what we're talking about, is just those magnetic moments and how they spin back and forth. If we look at the instrument, our electrons hide those nuclei. So that's why if we have varying amounts of electron density, that changes where it shows up on our chemical shift axis, that x-axis. If we look at the spectrometer itself, it's a giant magnet, and we'll get to giant here in a second, with our sample tube, and then we have the radio frequency, so our RF transmitter, and then we also have the detector that notes that kind of relaxation time. That then gets translated out to our printer, and that's where we're seeing the peaks. It's just kind of the basic components behind it. If we go through and look at these, that magnet, that whole system, that's this. Okay? And then this is the computer stuff that is now analyzing the data that comes out of it. Okay? So these are not particularly small instruments. That said, some of them are small. It just depends on how big a magnet you want to get to. So you'll notice the 850 on this one, that's 850 megahertz, so it's a really big magnet. We have an NMR in our lab that's 60 megahertz, so significantly smaller, and because of that now fits on the benchtop. Depending on where you go, you'll have varying size magnets. 850 is kind of a big one. Not all institutions have those. I think ASU's clears maybe 1,000. It's somewhere up there. It is very, very large. Okay, and it's a magnet, which I want to point out. The other kind of important thing on this is you notice this red kind of circle around it. That red circle is a warning, and typically you actually see it roped off, and that do not bring anything remotely magnetic within that range, because if it is magnetic, it's going to get stuck to the magnet. And particularly of relevance would be also credit cards. You don't want to bring credit cards near it because they can demagnetize the credit card. So kind of neat little features. And if we get excited about it sometime, maybe I'll tell you an interesting story about somebody potentially breaking one, which is not cheap. I think we're looking at several $1 million, if not tens of millions of dollars for a single instrument. So expensive stuff. When we look at the actual experiment, we're talking about the electrons shielding an individual atom. So we can talk about it as more or less shielded. But more or less shielded than what? We have to have a standard to compare to. So most spectra, or at least organic spectra, get compared to a compound known as tetramethylsilane. And it's added to most solvents so that we have an internal standard and we can now compare to that reference. And that reference is then defined as 0. So sometimes you'll see a peak at 0. That's referencing TMS. The rest of the peaks would be your sample. The organic protons should absorb in less shielded areas because TMS is very, very shielded. That's the as I point to the screen. That is the tetramethylsilane, which has a fairly large density of electrons around it. The next part is that our sample has to tumble or move within this. Okay? And that's because if we don't have a perfectly aligned structure, those magnetic fields are going to be at all sorts of different directions, and that could be potentially problematic if they can't move. If we allow the sample to freely move, that means we can average out those results and we get something known as a magic angle and stuff that's beyond me. But if you were interested, you could join a research group and study spectroscopy. So with that, it has to tumble and move, which would suggest that we really can only test liquids. That's kind of a limited role. So what we can do is we can make solutions. Okay, of course, downfield, some extra terms. So that solvent can be added to dissolve our samples so that our sample can freely move. There are active areas of research where you can actually run NMR on solid samples, but you need some more kind of context behind that. The standard organic sample is going to run through a solution, and that's where you're going to bring in chloroform or dimethyl sulfoxide. The problem with those is that your solid that has the hydrogens that we want to detect and chloroform or dimethyl sulfoxide both also bring in hydrogens. Well, if we look at the solute solvent concentrations, the solvent is going to be vastly more concentrated, which means chloroform as a solvent or even dimethyl sulfoxide can overwhelm the signal and we end up seeing nothing of our actual desired sample. So that is a bit of a problem, but that can be fixed. So what we can go through and do is replace the hydrogen atoms in each of our solvents with deuterium. Deuterium is not magnetically susceptible. So the nuclear spin doesn't align with the magnet and is NMR invisible, which means we don't see it in our spectra, which is fantastic. But there is something known as hydrogen exchange, and so you will typically see some signal from our solvents, and a lot of that depends on the purity and the cost and how well you took care of it. So for chloroform, you would typically see a signal at 7.26, which is a single peak for hydrogen, and then carbon NMR, because there's a carbon in it, you would see that at 77.2, and that would be a triplet. Okay, so you could see those signals pop up, and those are just due to solvent. DMSO is a little bit less frequently used, at least as far as our purposes, and in fact, for our purposes in our lab, we don't have deuterated DMSO, we only have deuterated chloroform. But it's going to have a slightly different chemical shift and a different pattern that you would then look for when trying to do your experiment. With that, we've kind of covered the big experimental observations, and that's about all I really wanted out of it, so cool. We'll move on to actual solving in just a minute.